Look up at the night sky and you'll see stars steady, unchanging, eternal. But what if I told you that some of those stars are hiding secrets far stranger than fiction? Among the most mysterious and breathtaking sights in the cosmos are planetary nebulas, glowing clouds of gas and dust that mark the dramatic final act of a star's life. These cosmic masterpieces aren't just beautiful, they're filled with bizarre, almost otherworldly discoveries that defy everything we thought we knew about how stars die. And today, we're diving deep into 30 of the strangest, most mind-bending revelations about these celestial wonders. Picture this: a star, much like our own sun, reaches the end of its life. Instead of fading quietly, it erupts in a spectacular display, casting off its outer layers in a swirling dance of color and light. What's left behind is a planetary nebula, a glowing shell of gas that can stretch light years across, shimmering with hues of electric blue, fiery red, and ethereal green. But here's the twist: these nebulas aren't just random clouds. They're sculpted by invisible forces, twisted into intricate shapes like hourglasses, butterflies, and even cosmic eyes staring back at us from the void. How do they form these impossible structures? Why do some of them seem to defy the laws of physics? The answers will leave you questioning everything you thought you knew about the universe. For centuries, astronomers believed planetary nebulas were simple, predictable phenomena. But the deeper we look, the more secrets we uncover, each one more astonishing than the last. Some of these nebulas harbor hidden stars locked in deadly gravitational dances, while others blast out jets of material at nearly the speed of light. There are nebulas that glow with mysterious, unexplained elements, and some that shouldn't exist at all based on our current understanding of stellar evolution. And that's just the beginning. From bizarre magnetic fields to rogue planets caught in the chaos, the truth about planetary nebulas is stranger than anything we could have imagined. So if you're ready to explore the unexplained, to venture into the heart of one of the universe's greatest mysteries, then buckle up, because what you're about to discover will change the way you see the night sky forever. Among all the strange and beautiful nebulas in the cosmos, few are as striking or as puzzling as the Butterfly Nebula. Officially catalogued as NGC 6302, this celestial masterpiece stretches its luminous wings across space, resembling a delicate butterfly mid-flight. But don't let its ethereal beauty fool you. What we're seeing here isn't just a random cloud of gas, it's the violent aftermath of a dying star, sculpted into this breathtaking shape by forces we're only beginning to understand. Most planetary nebulas form roughly spherical shells, like bubbles blown into space. So how did this one end up looking like a cosmic insect? The answer lies in its hidden heart. At the center of the Butterfly Nebula, a dying star isn't just shedding its layers, it's firing them outward in two opposing jets at nearly 600,000 miles per hour. These high-speed stellar winds collide with slower-moving material ejected earlier, compressing and shaping the gas into those iconic wing-like structures. But there's another player in this cosmic dance, an incredibly strong magnetic field, threading through the star's core like an invisible sculptor's hand. Astronomers believe this magnetic field acts like a cosmic funnel, channeling the star's outbursts into those narrow, symmetrical jets instead of letting them expand evenly. It's as if the star itself is directing its final act with precision, creating a spectacle that defies the usual rules of stellar death. Even stranger, the central star of NGC 6302 is one of the hottest ever discovered, blazing at over 400,000 degrees Fahrenheit. That's nearly 70 times hotter than our Sun, and it bathes the surrounding gas in intense ultraviolet light, causing it to glow with an almost otherworldly radiance. But here's where things get even weirder. The Butterfly Nebula isn't just pretty, it's practically a cosmic crime scene. Observations suggest the star at its center wasn't alone. There are hints of a companion star, possibly torn apart or swallowed by the dying giant, which could explain the nebula's extreme asymmetry. Some researchers think this violent stellar encounter might have even triggered the massive outburst that shaped the nebula in the first place. It's a reminder that even in death, stars can rewrite the rules and leave behind mysteries that keep us staring upward, searching for answers in the glow of their final breaths. If the Butterfly Nebula is a cosmic ballet, then the red Spider Nebula is a full-blown stellar hurricane. Catalogued as NGC 6537, this mesmerizing structure isn't just another dying star's farewell, it's a celestial tempest where winds scream through space at 300 kilometers per second. That's fast enough to race from Earth to the Moon in just 20 minutes, shredding the star's expelled gases into a labyrinth of fine, web-like filaments. But what could possibly unleash such fury? The answer lies in a star refusing to go quietly, its death throes rewriting the rules of stellar physics. Most planetary nebulas drift outward at a leisurely pace, their gases expanding smoothly like ripples on a pond. Not the red spider. Here, the central star, a white dwarf hotter than most welding flames, isn't just shedding its skin, it's violently ejecting material in supersonic bursts. These winds don't just move, they carve, etching intricate tendrils into the surrounding gas like a cosmic etcher's needle. Hubble images reveal filaments so finely detailed, they resemble neural pathways or lightning frozen mid-strike. And that's not just artistry, it's evidence of forces we still barely comprehend. What makes these winds truly baffling is their origin. Stars in their death throes typically lose mass gradually, like a slow leak. But the red spider's winds suggest something far more dramatic, perhaps a series of thermonuclear pulses ripping through the star's core, or a magnetic field so twisted it acts like a cosmic slingshot. Some theories even point to an unseen companion star, its gravity whipping the dying giant into a frenzy. Whatever the cause, these velocities defy textbook models of stellar evolution, forcing astronomers to question how such extreme energy is channeled without tearing the entire system apart. But the surprises don't stop there. Nestled within those crimson filaments are molecules that shouldn't survive such violence, complex carbon compounds clinging to existence amid the chaos. It's as if the nebula is simultaneously destroying and creating, a paradox that challenges our assumptions about the harshness of space. Even the nebula's temperature is a puzzle. While its core star scorches at nearly 500,000 degrees, the outer filaments glow relatively cool, hinting at layers of physics we've yet to untangle. The red Spider Nebula isn't just a spectacle, it's a cosmic laboratory, demonstrating how much we still have to learn about the universe's most violent finales. Every tendril, every gust of supercharged wind is a clue waiting to be decoded. And as telescopes grow sharper, one thing becomes clear. The more we study these chaotic masterpieces, the more we realize that the end of a star's life might be just as complex and astonishing as its beginning. Now shift your gaze to one of the most hypnotic sights in the cosmos, the Helix Nebula, a celestial bullseye so uncannily perfect it's earned the nickname, the Eye of Sauron. Officially catalogued as NGC 7293, this eerie structure stares back at us from across 700 light-years, its concentric rings glowing like ripples frozen in an interstellar pond. But these aren't just pretty patterns, they're a cosmic fingerprint, evidence of a dying star's final, rhythmic convulsions. What makes the helix so extraordinary isn't just its symmetry, it's the precision of those rings. Most planetary nebulas expand in chaotic bursts, leaving behind irregular clouds. Yet here, the gas forms near-perfect circles, spaced with almost mathematical regularity. Astronomers once assumed this was the work of a lone star shedding its layers in steady pulses. But the truth, this stellar swan song might actually be a duet. Hidden in the heart of the helix, there's mounting evidence of a binary companion, a second star whose gravitational tug could be conducting this cosmic symphony. Imagine a dying star convulsing as it burns through its final fuel. Every few thousand years, it coughs out a shell of gas like a smoker's rings blown into space. Now picture a smaller star orbiting close by, its gravity sculpting each expelled shell into crisp, even waves. This dance could explain the helix's startling geometry, the way its rings stack like tree rings, each layer marking another pulse of the dying star's agony. But there's a twist. The spacing between these rings doesn't match standard stellar models. Some shells are wider, others narrower, as if the star's death throes followed a secret rhythm we've yet to decipher. Then there's the nebula's ghostly glow. The helix's inner rings shine with an eerie blue-green hue, lit by the white dwarf's ultraviolet radiation. But farther out, the gas turns a haunting red, a sign of nitrogen molecules chilling to near absolute zero. This temperature gradient suggests the oldest rings have been expanding for tens of thousands of years, while newer ones are still warming up. It's like a layered timeline of stellar death, each ring a frozen snapshot of the star's final millennia. But here's where the mystery deepens. Recent observations reveal faint, braided structures within the rings, delicate filaments that shouldn't survive such violent origins. Some researchers speculate these could be scars from the companion star's gravitational kicks, or even evidence of planets torn apart during the chaos. Others propose magnetic fields, twisted like cosmic spaghetti, might be shaping the gas into these intricate forms. One thing's certain, the Helix Nebula isn't just a static relic. It's a dynamic, evolving puzzle, one that challenges us to rethink how stars die and what secrets they leave written in the sky. While most of the universe burns with the remnants of stellar fire, one nebula defies expectations by holding the title of the coldest natural place ever measured, the Boomerang Nebula. Located 5,000 light-years away in the constellation Centaurus, this hauntingly beautiful structure isn't just cold, it's colder than the void of space itself, chilling to a mind-numbing negative 272 degrees Celsius. That's just 1 degree warmer than absolute zero, the theoretical temperature where all molecular motion stops. How could a cosmic structure, born from the violent death of a star, become colder than the emptiness between galaxies? The answer lies in a physics phenomenon so dramatic, it's like watching a celestial air conditioner in action. What makes the boomerang so unique isn't just its record-breaking chill, it's the way it achieves it. Most planetary nebulas glow with residual heat from their dying stars, but this one acts like a cosmic refrigerator. The secret, a hyper-fast stellar wind. The central star, now a fading red giant, is ejecting gas at speeds exceeding 160,000 kilometers per hour, 10 times faster than typical stellar winds. This rapid expansion creates an effect similar to the way spraying compressed air from a can cools it down. As gas rushes outward, it spreads thin, robbing surrounding particles of energy and dropping temperatures to nearly the lowest possible in nature. But there's another twist. Unlike the chaotic outbursts seen in other nebulas, the boomerang's winds shoot out in two near identical, opposing jets, giving it that namesake boomerang shape. This symmetry suggests an invisible cosmic hand shaping the flow. Astronomers suspect an unseen companion star or an intensely focused magnetic field might be funneling the outbursts into these precise streams. The result, an eerie bow-tie structure where gas doesn't just drift, it practically flash freezes, creating a frosty halo that absorbs even the faint warmth of the cosmic microwave background, the afterglow of the Big Bang itself. Yet the real shocker isn't just how cold the boomerang is, it's how long it stayed that way. Most cooling nebulas eventually warm as they expand, but Hubble observations reveal this one has maintained its deep freeze for at least 1,500 years. That persistence hints at a sustained energy drain we still don't fully understand. Some theories propose dust grains in the nebula might act like microscopic refrigerants, while others point to shock waves recycling energy in ways that perpetuate the chill. The Boomerang Nebula challenges everything we thought we knew about stellar deaths. It's a reminder that even in the vacuum of space, nature can craft extremes that push the boundaries of physics. A place where a dying star doesn't just fade away, but leaves behind a ghostly fingerprint of cold unlike anything else in the universe. In the swirling tapestry of planetary nebulas, few structures captivate astronomers quite like the Southern Crab Nebula, a cosmic hourglass where two stars perform an intricate dance of creation and destruction. Catalogued as HEN 2104, this nebula doesn't just glow, it pulses with energy, sculpted into near-perfect symmetry by the relentless push and pull of its stellar heart. At first glance, it resembles a delicate hourglass suspended in space, its luminous loops stretching light years across the void. But this beauty hides a violent secret, a white dwarf and red giant locked in a gravitational embrace, their combined forces launching jets of material at speeds that defy imagination. What makes the Southern Crab so extraordinary isn't just its shape, it's the precision of its chaos. Most nebulas form haphazard clouds, but here, twin jets spiral outward with eerie coordination, like synchronized fountains of star stuff. The White Dwarf, a dense stellar corpse no larger than Earth, orbits its bloated red giant companion so closely that it siphons material from the giant's outer layers. As this stolen gas crashes onto the White Dwarf's surface, thermonuclear explosions blast it back into space not randomly, but in two opposing, laser-focused streams. The result, a nebula that looks less like an explosion and more like a meticulously engineered sculpture, its curves and loops tracing the rhythm of this deadly stellar tango. But here's the real shock. These jets aren't just traveling in straight lines. Observations reveal they're twisting, corkscrewing through space as the stars orbit one another, leaving behind helical trails that glow in vivid reds and blues. It's evidence of a system so finely balanced, the outflow direction shifts subtly over time, like a cosmic sprinkler spinning in slow motion. Such precision is vanishingly rare. Only a handful of nebulas exhibit this level of synchronized structure, making HEN 2104 a Rosetta Stone for understanding how binary stars shape their final acts. The Southern Crab's secrets don't stop there. Embedded within its glowing tendrils are molecules that shouldn't survive the violence of these jets' complex carbon chains and even traces of water vapor. Somehow, amid the chaos, conditions exist for chemistry as delicate as life's building blocks to persist. It's a reminder that even in death, stars can create pockets of cosmic wonder, challenging our assumptions about where and how the universe's most fragile structures might endure. Perhaps most tantalizing is what this system reveals about stellar fate. The White Dwarf's repeated thefts of its companion's material could one day trigger a supernova, a fate that might await many such pairs hidden in the cosmos. For now, though, the Southern Crab Nebula remains a fleeting masterpiece, a glimpse into the universe's ability to forge order from chaos, and proof that even in the darkest corners of space, there's artistry in the aftermath. Deep in the constellation Hydra, a phantom hangs in the cosmos NGC 3242, better known as the Ghost of Jupiter Nebula. This ethereal sphere of gas earned its nickname from its striking resemblance to the solar system's largest planet when seen through early telescopes. But modern observations reveal something far stranger. This nebula isn't just a static relic, it's flickering. Astronomers have clocked its brightness swinging dramatically over mere decades, a pace that defies everything we know about how planetary nebulas evolve. The culprit, a central star throwing tantrums of cosmic proportions, its death throws rewriting the rules of stellar retirement. What makes the Ghost of Jupiter so baffling isn't just its fluctuating glow, it's the speed of those changes. Most planetary nebulas fade over millennia, their light dimming as expanding gas disperses. Yet here, Hubble measurements show noticeable shifts in luminosity within human lifetimes. The key lies in the nebula's heart, where a white dwarf star no larger than Earth but weighing half our Sun's mass is caught in a cycle of violent helium shell flashes. Picture this: beneath the star's smoldering surface, a layer of helium ash ignites in sporadic thermonuclear outbursts, like a buried furnace flaring unpredictably. Each eruption floods the surrounding nebula with bursts of ultraviolet radiation, causing its gases to fluoresce brighter before settling back into gloom. These aren't gentle fluctuations. Spectroscopy reveals the star's temperature can swing by tens of thousands of degrees between outbursts, of volatility that challenges our models of white dwarf behavior. Normally, such stars cool steadily like dying embers, but the ghost central star seems stuck in a loop, reheating itself periodically as if refusing to fade quietly. Some theorists suggest it might be siphoning material from an unseen companion, while others propose exotic magnetic fields are trapping heat in its atmosphere. Either way, the result is a cosmic light show with no predictable schedule, turning this nebula into a celestial strobe light on a galactic scale. Then there's the nebula's structure, a series of concentric shells resembling tree rings, each marking a past outburst. The outermost layers, ejected over 12,000 years ago, drift lazily in the void, but closer in, newer shells show signs of being sculpted by recent explosions, their edges sharper and glow more intense. It's like peeling back layers of an onion, with each ring preserving a timestamp of the star's turbulent final millennia. Perhaps most intriguing are the chemical fingerprints hidden in the ghost shimmering gases. Unlike most planetary nebulas rich in hydrogen, this one's inner regions show bizarrely high concentrations of ionized helium and oxygen, a signature of material cooked at temperatures so extreme, atoms get stripped down to their bare nuclei. These are the echoes of a star burning its fuel not evenly, but in fits and starts, leaving behind a forensic trail in its glowing shroud. The ghost of Jupiter stands as a stark reminder that even in death, stars can cling to life in ways we're only beginning to comprehend. Its flickering glow challenges us to rethink what stellar afterlife really means: not a quiet fade to black, but a final act filled with false endings, dramatic encores, and mysteries that keep astronomers staring into the cosmic darkness, waiting for the next unpredictable flash. Among the countless planetary nebulas dotting the cosmos, none has shocked astronomers quite like the Stingray Nebula, a celestial infant caught mid-transformation. Catalogued as Hen 31357, this glowing structure holds the record as the youngest known planetary nebula, having burst onto the cosmic scene so recently that early telescope surveys barely registered its existence. In stellar terms, it's practically newborn, a mere blink since its central star began shedding its outer layers, and that's what makes it so extraordinary. This isn't just another aging star's swan song. It's a real-time laboratory showing us stellar death in unprecedented detail and forcing us to rewrite the textbooks on how quickly stars can unravel. When Hubble first photographed the Stingray in the 1990s, astronomers were stunned. Unlike the grand, intricate nebulas we're used to seeing, this one appeared faint and small, just a whisper of gas stretching a fraction of a light year across. But the real shock came when researchers compared these images to earlier observations. In the 1970s, the star at the nebula's heart hadn't yet begun its transformation. It was still a modest red giant, quietly burning through its fuel. By the 1980s, the first traces of ionized gas appeared, and by the 2000s, the nebula had taken full shape, its delicate wings of glowing material unmistakable. In cosmic terms, this evolution happened almost overnight. Most planetary nebulas take millennia to form, yet the Stingray went from invisible to fully formed in less than 50 years. What's happening at the Stingray's core is even more astonishing. The central star, now a white dwarf, isn't cooling gently like its older counterpart. It's heating up at a rate that defies all expectations. In just 3 decades, its temperature skyrocketed from a relatively cool 20,000 degrees to a blistering 60,000 degrees Celsius. That's like watching a campfire suddenly erupt into a blast furnace. This extreme heating ionizes the surrounding gas at breakneck speed, causing the nebula to brighten and expand in ways we've never witnessed before. Normally, this process unfolds over centuries. Here, it's playing out before our eyes, offering a front-row seat to stellar evolution's most dramatic act. But the real mystery isn't just how fast the stingray is changing, it's why. Most stars spend their final millennia in a slow, predictable decline. Yet something triggered this star's explosive finale with the subtlety of a detonation. Some researchers speculate the star might have ingested a nearby planet or companion star, disrupting its core's delicate balance. Others point to rare instabilities in its helium-burning shell, like a pressure cooker with a faulty valve. Whatever the cause, the stingray's rapid metamorphosis suggests stellar deaths can be far more spontaneous than we ever imagined, not always the slow fade we assumed, but sometimes a sudden, dazzling crescendo. Even the nebula's structure holds surprises. Unlike the chaotic clouds of older nebulas, the stingray's gas forms crisp, symmetrical loops, evidence of an unusually focused ejection. High-resolution images reveal delicate streamers and knots within these loops, hinting at shock waves rippling through the material as the young nebula interacts with surrounding space. And here's the kicker: the stingray's outer edges are already cooling, its outermost gases dispersing into the void almost as quickly as they formed. It's as if we're witnessing both the birth and the beginning of the end simultaneously, a cosmic lifetime compressed into human timescales. The Stingray Nebula challenges everything we thought we knew about stellar life cycles. It's proof that the universe can still spring surprises on us, that even processes we assumed were slow and stately can sometimes unfold with breathtaking speed. And as telescopes grow more powerful, who knows how many more of these cosmic infants will catch in the act, rewriting the story of stellar death one dazzling discovery at a time. If planetary nebulas are cosmic artworks, then the Cat's Eye Nebula is the universe's most intricate sculpture, a swirling labyrinth of nested shells and jagged spikes that looks more like a hallucination than a dying star's remains. Officially designated NGC 6543, this celestial masterpiece isn't just beautiful. It's a forensic record of stellar violence, with each layer revealing another chapter in its star's chaotic final millennia. What makes the Cat's Eye so mesmerizing isn't just its complexity, it's the sheer precision of its chaos. 11 concentric rings, each finer than an onion's skin, ripple outward from the core, while razor-sharp jets pierce through the glow like frozen lightning bolts. And here's the kicker: this structure shouldn't exist. Stars aren't supposed to die in such perfectly timed outbursts. Yet the Cat's Eye defies expectations, offering clues that the death of a sun-like star might be far more dramatic and far less predictable than we ever imagined. Peering into the heart of this nebula is like reading a stellar diary written in gas and light. Those delicate rings, each one represents a violent eruption, spaced roughly 1,500 years apart, as if the dying star coughed out its outer layers in rhythmic, almost clockwork convulsions. Normally, stars shed material steadily as they age, like a slow leak. But the Cat's Eye's layers suggest something far more explosive. A series of helium shell flashes, thermonuclear detonations beneath the star's surface that blasted entire atmospheres into space with terrifying regularity. Imagine a bomb rigged to explode every few millennia, each blast carving another glowing groove into the surrounding cosmos. That's the level of violence we're seeing etched into these shells. The real mystery, though, lies in those spikes. While most planetary nebulas expand smoothly, the Cat's Eye sports protrusions so sharp they look laser-cut. Hubble's close-ups reveal columns of dense gas stretching trillions of miles into space, relics of extreme magnetic activity during the star's death throes. Picture this as the star-ejected material. Its magnetic field spun like a frenzied top, funneling gas into narrow jets instead of letting it disperse evenly. These jets then plowed through earlier ejecta, leaving behind trails that glow like cosmic scratch marks. Even more bizarre, the spikes aren't just random. They align symmetrically, hinting at some unseen structure, perhaps a companion star's gravitational influence orchestrating the chaos like an unseen conductor. Then there's the nebula's core, where the white dwarf remnant burns hotter than the surface of our sun. Spectrographs reveal it surrounded by a halo of ionized oxygen, a fingerprint of temperatures so extreme they strip electrons from atoms. This energy doesn't just illuminate the nebula, it actively reshapes it, blowing vast bubbles in the older outer layers while compressing newer ones into intricate knots and filaments. The result is a dynamic, almost living structure where gas doesn't just drift, it dances, responding to forces we're still struggling to map. Perhaps most startling is what the cat's eye tells us about our own sun's fate. Conventional wisdom says stars like ours fade gently, puffing away their outer layers in a quiet stellar breeze. But NGC 6543 paints a different picture, one of fits and starts, a violent outburst separated by millennia of uneasy calm. If our sun has similar tantrums in its future, the solar system could one day be surrounded by its own version of these glowing, layered shells. A final masterpiece written in fire and gas, visible from galaxies away. Until then, the cat's eye remains both a warning and a wonder, proof that even the quietest stars might go out with a symphony of explosions, their deaths as complex and layered as their lives. No cosmic jewel shines quite like the Saturn Nebula, a glowing orb encircled by mysterious polar extensions that give it an uncanny resemblance to its planetary namesake. Officially catalogued as NGC 7009, this nebula doesn't just mimic Saturn's rings, it defies stellar physics with its bizarre, elongated lobes. Most planetary nebulas expand uniformly, but the Saturn Nebula's structure reveals something far stranger. Two jet-like protrusions shooting from its poles, as if an invisible hand stretched the gas into cosmic horns. These aren't random formations, they're the result of a dying star spinning at breakneck speeds, its magnetic fields whipping expelled material into precise, symmetrical shapes. At the heart of this celestial spectacle lies a white dwarf spinning so fast it completes a full rotation every few hours, a dizzying pace for a stellar corpse. As the star shed its outer layers, this rapid spin acted like a cosmic centrifuge, flinging material outward along its equator while powerful magnetic fields funneled additional gas toward the poles. The result, a nebula with a double-layered structure, a dense equatorial ring resembling Saturn's iconic rings, and those enigmatic polar jets stretching light years into space. But here's what baffles astronomers. The lobes glow brighter than expected, suggesting they're not just passive outflows. They're being superheated by shocks or radiation we don't fully understand. Delving deeper, Hubble's sharp eye reveals these lobes are anything but smooth. They're studded with knots and filaments like beads on a cosmic string, each one marking a violent collision between the star's high-velocity winds and slower-moving material ejected earlier. Spectroscopy uncovers another surprise. The lobes contain unusual concentrations of neon and oxygen, elements typically forged deep in a star's core. Their presence here implies the dying star didn't just gently shed its surface, it convulsed, dredging up inner material and launching it into space with tremendous force. The real puzzle is how these structures maintain their precision over vast distances. Magnetic fields likely play a role, acting like cosmic rails to keep the jets tightly collimated. But recent observations suggest another player, the ghostly influence of a companion star or substellar object, its gravity subtly shaping the outflow. Whether through magnetism, spin, or unseen partners, the Saturn Nebula stands as proof that even in death, stars can sculpt their legacies with an artist's precision. leaving behind not chaos but hauntingly ordered beauty. What makes NGC 7009 truly groundbreaking is its challenge to stellar models. Theorists struggle to simulate how such extreme rotation and magnetic fields persist in a dying star, let alone how they sculpt gas with this level of geometric control. Every new observation peels back another layer, revealing a universe where the rules of stellar demise are far more intricate and far more breathtaking than we ever dreamed. Hidden in the constellation Cygnus lies one of the most chemically bizarre structures in the cosmos, the Jewel Bug Nebula, a glowing enigma officially catalogued as NGC 7027. Unlike most planetary nebulas where gas disperses rapidly into space, this one clings to its molecular riches with startling tenacity. At its heart lies a treasure trove of dense molecular hydrogen, a discovery that sent shockwaves through astrophysics. Planetary nebulas aren't supposed to harbor such pristine gas clouds. They're meant to be ionized graveyards where ultraviolet radiation from the central star shreds molecules apart. Yet here, vast reservoirs of intact hydrogen molecules thrive, forcing scientists to confront a glaring question: how does anything survive the stellar inferno at this nebula's core? The answer lies in NGC 7027's explosive history. High-resolution images reveal a nebula within a nebula, an inner shell of blistering hot gas cocooned inside a cooler, clumpy outer envelope. This layered structure acts like a stellar bunker, shielding pockets of molecular gas from the white dwarf's deadly radiation. Imagine a snowstorm trapped inside a double-paned oven window. The inner pane takes the brunt of the heat while the outer layer preserves delicate frost patterns. That's essentially what's happening here on a cosmic scale, but the real twist: these molecular clouds aren't just passively hiding, they're actively forming. Radio telescopes have detected telltale emissions from hydrogen molecules caught in the act of assembling, suggesting this nebula isn't just preserving chemistry, it's fostering it. What makes this discovery revolutionary isn't just the presence of molecular hydrogen, it's the sheer amount. NGC 7027 holds approximately 10,000 times the mass of Earth in molecular gas, a staggering quantity that defies conventional models of planetary nebula evolution. Standard theory predicts such molecules should have been obliterated within a few thousand years of the star's death throes. Yet the Jewel Bug's outer layers have sheltered them for over 600 years and counting. This longevity implies planetary nebulas might play an unexpected role in the galactic ecosystem, not just as recyclers of stellar material, but as temporary safe zones where complex chemistry can persist against all odds. Then there's the nebula's bizarre shape, which looks less like a dying star's remains and more like a shattered gemstone. Its irregular, polygonal structure suggests multiple outbursts from different stellar latitudes, creating overlapping shock fronts that carve the gas into crystalline-looking facets. Within these jagged boundaries, the molecular gas clusters in dense knots, some so compact they're beginning to collapse under their own gravity, a process normally seen in star-forming regions, not stellar graveyards. It's as if the nebula can't decide whether it's ending one stellar life or seeding new ones, blurring the line between death and rebirth. Perhaps most intriguing is what the Jewel Bug tells us about our own cosmic neighborhood. The same molecular hydrogen that makes up NGC 7027's resilient clouds is the raw material of stars and planets. If other planetary nebulas harbor similar hidden reservoirs, they could be scattering enriched molecular material across galaxies, contributing to the chemical diversity we see today. Far from being mere stellar tombstones, these glowing shells might actually be galactic gardeners, planting seeds for future solar systems even as their parent stars fade into darkness. The Jewel Bug Nebula doesn't just challenge our assumptions, it rewrites the entire narrative of stellar afterlife, proving that in the cosmos, even death can be a creative force. Most planetary nebulas glow with the soft light of fluorescing gases, but not the blue snowball. Catalogued as NGC 7662, this radiant celestial sphere hides a violent secret: it's emitting X-rays. That's right, the same high-energy radiation typically associated with black holes and supernova is pouring from what looks like a serene blue orb. This discovery sent astrophysicists scrambling because standard models say nebulas like this shouldn't produce X-rays at all. So what's really happening inside this deceptively peaceful-looking structure? The answer involves shockwaves hotter than 1,000,000 degrees, stellar winds colliding like cosmic tsunamis, and a white dwarf that refuses to fade quietly into the night. At first glance, the blue snowball lives up to its name, a near-perfect sphere of ionized oxygen and nitrogen glowing with an almost ethereal azure hue. But Chandra X-ray observatory data reveals an invisible inferno at its core. Unlike the gentle ultraviolet radiation that illuminates most planetary nebulas, this one's central star is generating violent X-ray emissions, signaling temperatures in the millions of degrees. The culprit, a brutal collision between two stellar winds. Here's how it works. As the dying star shed its outer layers, it first expelled a slow-moving wind of material, drifting outward at a leisurely pace. Later, as the exposed core heated up, it unleashed a second wind, this one screaming into space at several thousand kilometers per second. When this supersonic outflow smashed into the slower-moving gas, the impact created shockwaves so powerful they heated the gas to X-ray emitting temperatures, like a cosmic sonic boom igniting the surrounding atmosphere. What makes NGC 7662 truly exceptional is the clarity of these shock boundaries. Most planetary nebulas mix their winds chaotically, blurring any evidence of collisions. But here, the X-rays trace razor-thin edges where the winds meet, mapping the violence with startling precision. It's as if the nebula froze this stellar storm mid-explosion, giving us a snapshot of physics normally too turbulent to study. Even more intriguing, these X-rays aren't uniform. They cluster in arcs and loops, suggesting the central star's winds didn't blow steadily, but in pulses like a celestial engine misfiring. Some researchers speculate this unevenness might hint at a companion star's gravitational tugs, stirring the winds into irregular patterns. Then there's the nebula's central star itself, one of the hottest white dwarfs known, blazing at nearly 200,000 degrees. Spectroscopy reveals it's not just sitting idle. It's still actively ejecting material, its fierce winds peppering the nebula's inner walls with enough energy to keep the shockwaves crackling. This sustained activity challenges assumptions about how quickly stellar corpses cool. According to textbooks, white dwarfs should settle into quiet retirement after ejecting their nebulas. But the blue snowball star is anything but retired. It's more like a retiree who traded golf clubs for a jetpack. The implications stretch far beyond this one glowing sphere. If X-ray emissions can arise in such a seemingly placid nebula, how many others harbor hidden high-energy processes? Recent surveys suggest the blue snowball might not be alone. Several similar nebulas now show faint X-ray signatures, hinting at a previously overlooked phase of stellar death. It's a reminder that even the quietest corners of the cosmos can conceal unimaginable violence, and that every time we think we've figured stars out, they find new ways to surprise us. The blue snowball's serene glow isn't just a farewell, it's a cosmic smokescreen, behind which the laws of physics are staging their most spectacular fireworks. Few cosmic dances are as mesmerizing or as perfectly timed as the celestial ballet playing out at the heart of the Twin Jet Nebula. Officially known as M29, this breathtaking structure spreads its iridescent wings across 2.3 light-years, each lobe glowing with the eerie blue-green light of fluorescing oxygen. But what makes this nebula truly extraordinary isn't just its beauty, it's the precision of its symmetry, a mirror-like perfection that points to an invisible choreographer. A pair of stars locked in a gravitational embrace so intimate, their movements sculpt the very fabric of the nebula around them. At the center of this cosmic spectacle, a white dwarf and its companion star whirl around one another every 120 years, their orbital dance generating forces powerful enough to launch two opposing jets of gas at speeds exceeding 320 kilometers per second. These aren't chaotic outbursts, they're tightly collimated beams, funneled into narrow streams by the binary system's combined gravity and spin. Imagine two figure skaters clasping hands and spinning faster and faster until ribbons of ice shoot from their fingertips. That's the level of coordination happening here, but on a scale where the ribbons stretch trillions of miles across space. Hubble's razor-sharp images reveal the mechanics behind this precision. As the dying star shed its outer layers, its companion's gravity caught the material, flattening it into a dense accretion disk. But instead of spilling outward evenly, the disk funnels gas toward the star's rotational poles, where magnetic fields launch it into space like twin fire hoses. The result, those iconic wings, each one a time capsule of stellar material ejected in perfect synchronicity with the star's orbit. Spectroscopy adds another layer of wonder. The jets aren't steady flows but periodic pulses, their chemical fingerprints revealing bursts of activity aligned with the binary pair's closest approaches. What truly baffles astronomers, though, is how these structures maintain their symmetry over such vast distances. Normally, interstellar winds or magnetic turbulence would distort the jets, yet M29's wings remain flawlessly matched. The secret may lie in the system's extreme stability. The star's orbit is so finely balanced that their combined gravitational field acts like a cosmic railgun, keeping the outflows aligned even as they cross light years of space. Recent observations even suggest the white dwarf's intense radiation is ionizing the jet's edges, creating shimmering cylindrical sheaths that further stabilize their path. Then there's the nebula's eerie searchlight effect, bright knots of material that appear to move outward over time, like celestial breadcrumbs tracing the jet's expansion. These aren't just static features, they're evidence of shock waves rippling through the outflows, created when faster-moving material plows into slower ejecta. By tracking these knots, astronomers have reconstructed the nebula's entire eruption history, revealing periods of violent activity interspersed with eerie calm, a testament to the star's unpredictable relationship. The Twin Jet Nebula challenges our notions of how binary systems evolve. Conventional models struggle to explain how such delicate symmetry persists amid the chaos of stellar death. Yet here it is, a glowing testament to the universe's ability to forge order from chaos, proving that even in the darkest corners of space, there's artistry in the interplay of gravity, spin, and time. As telescopes peer deeper into these dancing stars' secrets, one thing becomes clear. When it comes to stellar finales, sometimes the most breathtaking shows are the ones performed in perfect unison. The Calabash Nebula isn't just another dying star's farewell, it's a cosmic train wreck unfolding in real time. Known to astronomers as OH231.8, this chaotic structure earned its nickname from the bizarre, lumpy shape that makes it look like a gourd flung into space. But the real shocker isn't its appearance, it's the scent. Spectral analysis reveals clouds of sulfur compounds so dense, researchers joke it's the universe's largest rotten egg. And that stench is more than just cosmic trivia. It's a forensic clue pointing to explosions violent enough to rip apart molecules and forge new ones in the crucible of stellar death. What makes the Calabash extraordinary isn't just its chemistry, it's the sheer violence of its transformation. Unlike most planetary nebulas that form gradually, this one's central star is caught mid-eruption, blasting material outward in convulsive fits. Hubble images capture the aftermath. Vast lobes of gas racing outward at 700,000 kilometers per hour, while dense clumps near the core lag behind like debris from a bomb blast. The result, a nebula that looks less like a smooth bubble and more like shrapnel frozen mid-explosion. For astronomers, it's a rare chance to study stellar death in its messy, unvarnished reality, not the polished aftermath we usually see. Those sulfur clouds tell the darkest part of the story. Normally, sulfur binds with hydrogen to form hydrogen sulfide, the compound responsible for rotten eggs' infamous odor. But in the calabash's turbulent environment, ultraviolet radiation and shock waves tear these molecules apart, leaving behind exotic sulfur ions that glow in eerie infrared hues. Some of these fragments even recombine into sulfur monoxide, a molecule so reactive it rarely survives in space. Their presence here is like finding gunpowder residue at a crime scene, proof of explosions powerful enough to rewrite chemistry itself. Yet the chaos doesn't stop there. Buried in the nebula's heart, ALMA radio telescope data reveals a sprawling disk of dust and gas, the crumbling remains of the star's outer layers. This disk spins at a dizzying pace, funneling material into jets that punch through the surrounding chaos like cosmic blowtorches. The twist: these jets wobble unpredictably, their paths warped by the dying star's erratic convulsions. It's as if the star's final death throes are so violent, even the laws of physics struggle to keep up. The Calabash Nebula forces us to confront an uncomfortable truth: stellar death isn't always graceful. Sometimes it's a demolition derby of shock waves, magnetic chaos, and chemical alchemy, a reminder that even in the quiet of space, nature's most breathtaking spectacles often come from its most destructive impulses. And as telescopes peer deeper into this cosmic wreckage, one thing becomes clear: what looks like an ending might just be the universe's way of stirring the pot, mixing the ingredients for whatever comes next. Gemstones aren't just found in Earth's crust, they're scattered across the cosmos, strung together in a celestial display of unimaginable scale. Behold the Helix Nebula, officially catalogued as PNG 054.203.4, where a dying star has crafted a glowing loop of cosmic diamonds. This isn't poetic exaggeration, it's astrophysics in its most dazzling form. Each gem in this interstellar necklace is a dense knot of gas, heated to incandescence by the violent dance of two stars locked in a gravitational embrace so tight it's tearing one of them apart. The story begins with a binary system that's been orbiting in harmony for billions of years until one star reached the end of its life. As it swelled into a red giant, its outer layers crept dangerously close to its smaller companion. That's when chaos erupted. The smaller star, unable to escape the growing giant's pull, found itself spiraling inward, its gravity shredding the dying star's atmosphere like a cosmic blender. The result: a luminous ring of stellar material studded with jewel-like clumps, each one a droplet of superheated gas compressed by shockwaves into radiant orbs. But here's the twist: these aren't random formations. The diamonds align with mathematical precision, spaced almost evenly around the nebula's circumference. This symmetry points to a phenomenon called Rayleigh-Taylor instability, the same physics that causes a stream of falling water to break into droplets. In this case, the smaller star's gravity acted like a celestial sculptor, kneading the expelled gas into regular intervals as it orbited at breakneck speed. Hubble's close-ups reveal even finer detail. Some knots glow brighter than others, their cores so dense they've begun forming molecules, carbon monoxide, and even traces of water vapor in the hostile environment of deep space. What makes the necklace truly unique is its central engine. Most planetary nebulas are powered by a single white dwarf, but here the core still hosts both stars. The white dwarf remnant and its surviving partner, now circling each other in a frantic pirouette every 1.2 days. Their mutual gravity doesn't just shape the nebula, it supercharges it. Ultraviolet radiation from the white dwarf excites the surrounding gas, causing it to fluoresce in vibrant hues of blue and green, while the companion star's relentless motion stirs the pot, preventing the nebula from dissipating into the void. This system is more than just a pretty face, it's a time capsule. The nebula's expanding ring lets astronomers calculate the exact moment the red giant met its demise, roughly 10,000 years ago. And those diamond-like knots, they're racing outward at 50 kilometers per second, carrying with them chemical fingerprints of the star's final convulsions. Among them are rare isotopes of nitrogen and oxygen elements forged in the star's core and dredged up during its death throes, now forever preserved in these glowing celestial gemstones. The Helix Nebula challenges our notions of stellar endings. It's proof that even in destruction, the universe has a flair for artistry, and that sometimes the most breathtaking sights emerge from the most violent cosmic collisions. As telescopes peer deeper into its glittering structure, one thing becomes clear: this isn't just a nebula. It's a monument to the forces that shape the cosmos, written in gas, light, and the stubborn persistence of beauty amid chaos. The Medusa Nebula slithers across the cosmos with a ghostly presence, its delicate tendrils so faint they eluded detection for decades. Officially catalogued as Able 21, this celestial spectre earned its mythological name not just for its serpentine shape, but for the challenge it poses to observers. A nebula that stares back at you, not with the fiery glow of younger counterparts, but with the dim whispers of a stellar ghost. What makes this structure so ethereal isn't just its age. Though at an estimated 9,000 years old, it's among the oldest known planetary nebulas, but the quiet resignation of its dying star, which shed its layers so gently that the resulting nebula barely glows at all. Unlike the neon brilliance of younger nebulas, the Medusa's light comes from anemic ionization, just enough ultraviolet radiation to tease a faint shimmer from its oxygen atoms. The central star, now a cooling white dwarf, burned out its high-energy fuel long ago, leaving it unable to aggressively ionize its surroundings. Imagine a fluorescent bulb flickering on its last legs. That's the Medusa's glow, a pale greenish hue detectable only through long exposure photography. Even Hubble struggles to capture its full structure without painstaking observation. This isn't just a dim nebula, it's a cosmic fossil, its delicate filaments preserving the dying breaths of a star that exhausted itself not with a bang but an exhausted sigh. Yet the Medusa's faintness hides an ironic twist. Its visibility is a paradox. The same factors that make it hard to detect low ionization and expansive, thin gas are what allow us to see its full structure. Younger nebulas often appear as blinding disks, their dense gases obscuring internal details. But here, the star's leisurely mass loss over millennia left behind a wispy, transparent shroud. Telescopes peer straight through its outermost layers, revealing intricate loops and braids normally hidden in more energetic nebulas. These filaments aren't random. They're a stellar autopsy report, mapping the star's final millennia of pulsations with forensic precision. Each ripple corresponds to a past convulsion, now frozen in gas as the nebula dissipates into the interstellar void. What truly fascinates astronomers, though, is how the Medusa defies the typical planetary nebula life cycle. Most luminous nebulas fade within 20,000 years as their gases disperse. Yet Able 21's ancient age suggests it's clinging to existence far longer than models predict. The secret may lie in its environment. This ghost drifts through a sparser region of space, where fewer interstellar winds buffet its fragile structure. It's a reminder that celestial objects don't expire by a universal clock, but according to the unique conditions of their demise. The Medusa's faint glow isn't just a footnote, it's a whisper from the universe's quieter corners, proving that even in the grand theater of stellar death, some stars exit not with fireworks, but with a slow, haunting fade to black. Among the countless planetary nebulas adorning our galaxy, Cronberger 61 stands out like a cosmic work of art, a sphere so perfectly symmetrical it's been nicknamed the soccer ball nebula. Glowing faintly in the constellation Cygnus, this celestial orb defies the usual chaotic shapes of stellar death, presenting instead a near-flawless bubble of ionized gas. Such geometric precision is staggeringly rare in nature, where asymmetry tends to rule. So how did a dying star manage to craft what looks like a celestial firework frozen mid-burst? The answer might rewrite our understanding of how stars shed their outer layers, and whether such perfection is a stroke of cosmic luck or the signature of something far more deliberate. Most planetary nebulas resemble abstract paintings swirling, lopsided clouds sculpted by magnetic fields, companion stars, or uneven stellar winds, but the soccer ball structure suggests an entirely different process. Hubble images reveal concentric shells of gas expanding outward with almost mathematical regularity, like ripples from a stone dropped in perfectly still water. This isn't just aesthetic, it's evidence of a star that ejected its atmosphere in controlled, uniform pulses rather than the violent, haphazard outbursts we typically see. The leading theory, a star so finely balanced that it shed mass evenly from all points on its surface, as if its entire outer layer peeled away in one synchronized motion. Yet achieving such symmetry requires conditions so precise they border on miraculous. For a nebula to form this way, the dying star would need an unusually calm demise. No disruptive binary companion, no lopsided magnetic fields, no turbulent convection zones beneath its surface. It's the astrophysical equivalent of blowing a soap bubble without a single gust of wind to distort it. Some researchers argue this points to a rare class of stars with exceptionally stable outer layers, where radiation pressure gently pushes material outward in all directions equally. Others propose an even wilder idea. Cronberger 61 might be the product of a merger where two stars coalesced into one so smoothly, their combined mass ejection settled into this eerie symmetry. The real mystery lies in the nebula's faint outer halos. Infrared observations reveal older, dimmer shells surrounding the soccer ball's bright core, each one a fossilized record of the star's earlier mass loss. These layers are spaced at near regular intervals, suggesting the star didn't just die evenly, it did so in rhythmic bursts, like a metronome ticking off its final millennia. What could trigger such clockwork precision? Pulsations in the star's helium-burning shell might explain it, but models struggle to replicate the timing. It's as if the star's interior played conductor to its own demise, orchestrating each ejection with impossible consistency. Debate still rages over whether Cronberger 61 is a cosmic fluke or a signpost to undiscovered physics. If it's pure chance, we'd expect to find fewer than 1 in 10,000 nebulas this symmetrical. Yet recent surveys hint at more spherical nebulas than predicted, lurking faintly in the galactic outskirts. Could there be a yet unrecognized stellar death pathway that favors perfect geometry? The soccer ball nebula doesn't just challenge our eyes, it challenges our textbooks, daring us to consider that even in the chaos of stellar death, nature sometimes chooses order. And if we can unravel how it happened here, we might just find similar perfection hiding in plain sight elsewhere in the cosmos. The Ant Nebula defies cosmic logic with its bizarre, insect-like symmetry, a structure so precise it looks engineered rather than born from chaos. Officially designated Menzel 3, this celestial wonder stretches 6 light-years from wingtip to wingtip, its glowing lobes resembling an ant's segmented body frozen mid-scuttle. But what makes this nebula truly mind-bending isn't just its shape, it's the supersonic jets carving those pathways with surgical precision, blasting outward at nearly 1,000 kilometers per second. These aren't the haphazard outbursts of a dying star, they're cosmic laser beams cutting through interstellar space with barely any dispersion across staggering distances. At the heart of this precision lies a white dwarf spinning so fast it completes a full rotation every few hours, a stellar dynamo whipping its magnetic fields into frenzy. As the star shed its outer layers, these fields funneled the escaping material into 2 narrow beams, like water forced through a spinning garden sprinkler. But here's where physics gets weird. Those jets aren't just straight lines. Hubble observations reveal subtle S-shaped curves in their trajectories, evidence that the central star isn't just spinning, it's wobbling like a top losing stability. This precession, as astronomers call it, causes the jets to trace spirals through space, sculpting the nebula's iconic antennae into their elegant arcs. What's even stranger is how these jets maintain their focus. Interstellar space is littered with particles that should scatter and diffuse such narrow outflows over light years. Yet Menzel 3's beams remain collimated with almost impossible tightness. The secret may lie in the jet's own turbulence. Paradoxically, the same forces that should disrupt them might also generate magnetic sheaths around their edges, acting like cosmic insulation to keep the flows razor straight. It's akin to how a laser stays coherent by creating its own waveguide, except here, the universe is improvising with stellar winds and magnetism instead of mirrors. Then there's the nebula's eerie silence. Most high-speed jets generate shockwaves that light up surrounding gas like neon signs. But the Ant Nebula's lobes glow faintly, their energy oddly muted. Spectrographs reveal why. The jets aren't plowing through static gas, they're racing ahead of the star's earlier, slower ejections, slipping through like hot knives through butter. Only at the very tips, where the jets finally catch up to denser interstellar material, do they ignite visible shock fronts, those bright antennae that give the nebula its name. The rest is a ghostly trail, a whisper of momentum preserved across millennia. Perhaps most perplexing is what the Ant Nebula suggests about stellar depth's diversity. Textbook models assume planetary nebulas form when stars gently shed their skins. But Menzel 3's extreme symmetry screams something else entirely, a death so controlled, so dictated by spin and magnetism, it borders on orchestration. It forces us to question whether we've underestimated how stars wield their final moments, transforming chaos into geometry on a scale that dwarfs human comprehension. In the Ant Nebula's case, the cosmos isn't just ending a star, it's signing its name with jets of fire, leaving behind a masterpiece that will outlive civilizations. The Eskimo Nebula stares back at us with an almost playful defiance, its intricate, fur-lined hood of radiant spikes giving it an uncanny resemblance to a face peering out from the depths of space. Catalogued as NGC 2392, this celestial wonder isn't just another pretty cosmic cloud, it's a labyrinth of physics-defying filaments, each one a thread in the universe's most elaborate winter coat. What creates this bizarre, hairy texture? The answer lies in a battle between heat and gravity so finely balanced, it's as if the nebula itself is walking a thermal tight beam. At first glance, the Eskimo's iconic Parker hood appears as a series of radial spikes like sunbeams frozen mid-emission. But Hubble's close-ups reveal something far stranger. Each filament is actually a rope of denser gas, twisted and braided by forces we're only beginning to understand. These aren't random wisps, they're the aftermath of thermal instabilities, where pockets of cooling gas collapse under their own weight while hotter material surges around them. Imagine blowing on a bowl of steaming soup. The rising heat creates ripples on the surface as cooler droplets fall back. In the Eskimo Nebula, this same dance plays out on a cosmic scale, with gravity sculpting the falling cool gas into those distinctive hairy tendrils. What makes this nebula truly extraordinary is the precision of its chaos. The filaments aren't just clumps, they're arranged in near-perfect radial symmetry, fanning outward from the central star like spokes on a wheel. This suggests the instabilities aren't random. They're orchestrated by the dying star's rotation or magnetic field, creating regular zones where gas can condense. Spectroscopy adds another layer to the mystery. The filaments glow brighter in certain wavelengths, hinting at chemical variations that might act like cosmic refrigerants, accelerating cooling in select regions. It's as if the nebula has built-in thermal triggers, flipping switches to sculpt its own intricate texture. Then there's the central star's role, a white dwarf so hot, its ultraviolet radiation should be vaporizing these delicate structures. Yet the filaments persist, their survival likely due to sheer density. Each hairy spike packs enough mass to withstand the stellar onslaught, like trees bending but not breaking in a hurricane. Even more puzzling, the filament's motion. ALMA telescope data shows them expanding outward at different speeds, some lagging behind as if caught in invisible currents. This could be evidence of shock waves rebounding through the nebula, or perhaps the gravitational echoes of a long-dead companion star stirring the pot. The Eskimo Nebula doesn't just challenge our eyes, it challenges our models. Textbook thermal instability theories struggle to explain how such intricate patterns emerge across light years. Yet here they are, a frozen snapshot of physics in its most artistic mood. Every filament is a cipher, waiting to be decoded, a reminder that even in the cold depths of space, the universe has a flair for textures that defy imagination. And as telescopes peer deeper, one thing becomes clear. This cosmic parka isn't just keeping its secrets warm, it's daring us to unravel them one thread at a time. Gaze into the heart of the Owl Nebula, and two shadowy voids stare back. Dark patches so perfectly placed they evoke the unblinking eyes of a nocturnal predator. Catalogued as M97, this cosmic illusion isn't just a trick of perspective. It's a masterclass in how nature sculpts shadow from chaos. Those eerie eyes aren't empty space. They're dense knots of gas so thick they absorb the nebula's own light, casting in Chi silhouettes against the glowing backdrop. The result, one of the most striking examples of pareidolia in the cosmos, where random structures trick our brains into seeing familiar shapes. But the real magic lies in how uneven physics creates this avian mirage. Most planetary nebulas glow with relatively uniform light, their gases dispersed evenly by stellar winds. The Owl defies this expectation with dramatic chiaroscuro regions of brilliance slashed by abrupt darkness. Hubble's keen eye reveals why. The nebula's outer shell isn't smooth. It's pockmarked with clumps of molecular hydrogen and dust, some so dense they block 99% of the light behind them. These knots formed as the dying star's outer layers cooled unevenly, fragmenting like drying mud under a summer sun. But here's the twist, their owl-eye alignment isn't pure chance. The two largest patches sit at opposing edges of an invisible bubble, a relic of the star's equatorial plane where material naturally congregates thicker during its death throes. What makes these shadows truly mesmerizing is their dynamic nature. Far from static blobs, they're expanding at 7 kilometers per second, stretching the pupils wider over millennia. Spectroscopy uncovers another layer. The eyes aren't just absorbing light. They're fluorescing faintly in infrared as embedded molecules re-radiate stolen energy at longer wavelengths. It's as if the owl is winking at us in light we can't see, its gaze transcending the visible spectrum. Yet the illusion's perfection hides a violent origin. The owl's central star, now a white dwarf, didn't shed its layers gently. Observations suggest violent thermal pulses, sudden eruptions that ejected material in convulsive bursts, creating the density variations that now haunt its ghostly face. Those iconic dark patches, they're the scars of stellar indigestion, moments when the star couldn't expel its atmosphere evenly. Even the nebula's faint outer halo, visible only through long exposures, tells a story of past outbursts, each one leaving behind chemical fingerprints now frozen in the expanding glow. The Owl Nebula challenges our perception of cosmic artistry. It's proof that beauty in the universe isn't just about what shines sometimes, it's the carefully carved absences that captivate us most. And as telescopes peer deeper into those Inkai eyes, they reveal something profound. Darkness isn't always emptiness. It can be a canvas shaped by physics into forms that speak directly to our humanity, connecting the alien vastness of space to the familiar patterns of home. Floating in the cosmic void like a slice of lemon suspended in space, the IC 3568 Nebula, better known as the lemon-sliced nebula, defies nature's usual preference for asymmetry. Its edges are so crisp, so unnaturally precise, they look like they've been cut with celestial scissors rather than forged in the turbulent chaos of a dying star. Unlike the swirling, irregular shapes of most planetary nebulas, this one's boundary is a near-perfect circle, a geometric marvel that glows with an almost artificial sharpness against the blackness of space. So how does something so orderly emerge from the inherently messy process of stellar death? The answer lies in a delicate dance between radiation, speed, and the ghostly hand of an invisible cosmic sculptor. What makes the lemon slice's crisp edges so baffling isn't just their shape, it's their defiance of time. Most planetary nebulas blur as they expand, their gases gradually dispersing into the interstellar medium like ink dropped in water. But IC 3568's boundary remains startlingly sharp even after millennia of expansion, suggesting something is actively maintaining its structure. The secret may lie in the nebula's blistering central star, a white dwarf so hot it bathes the surrounding gas in a relentless torrent of ultraviolet radiation. This energy doesn't just illuminate the nebula, it ionizes the gas at its outer edge, creating a visible wall where atoms absorb and re-emit light with textbook efficiency. Think of it like the surface of a soap bubble. The shell appears crisp because light refracts uniformly at its edges, even though the underlying film is vanishingly thin. But radiation alone can't explain the lemon slice's pristine geometry. The nebula's symmetry hints at another player, a remarkably even ejection of material during the star's death throes. Unlike stars that cough out their atmospheres in fits and starts, this one seems to have shed its outer layers in a smooth, spherical pulse, almost as if its entire surface peeled away in one synchronized motion. Supporting this theory are faint concentric rings just inside the nebula's edge, revealed by Hubble's sensitive instruments. These ripples, spaced like tree rings, suggest the star expelled its gas in rhythmic waves rather than a single explosive burst. Each wave compressed the one before it, stacking neatly like layers of an onion and reinforcing the nebula's structural integrity over time. Yet even this doesn't fully account for the lemon slice's razor-sharp boundary. The interstellar medium is anything but empty. It's filled with stray atoms, dust grains, and magnetic fields that should erode and distort such a perfect sphere. That's where a third factor comes into play: speed. Observations show the nebula's outer shell is expanding at a brisk 20 kilometers per second, outpacing the typical drift of surrounding material. This velocity creates a sort of bow shock effect, where the nebula's leading edge plows through space like a ship's prow, sweeping aside potential disruptors before they can blur its outline. The result, a self-cleaning cosmic bubble, its edges kept pristine by sheer momentum. The lemon-sliced nebula isn't just a pretty oddity, it's a challenge to our assumptions about stellar deaths. Its geometric perfection suggests that under the right conditions, chaos can give way to order, and randomness can yield near mathematical precision. As telescopes continue probing its secrets, one thing becomes clear: the universe doesn't always play by the rules we expect. Sometimes it serves up a slice of cosmic perfection so flawless, it leaves us questioning whether we've glimpsed nature's handiwork or something even more extraordinary. Don't let the name fool you. The Little Dumbbell Nebula is anything but simple. Catalogued as M76, this cosmic structure might look like a petite twin-lobed bubble at first glance, but peer closer, and its deceptive nickname unravels into a tapestry of stellar chaos. Far from being a neat pair of symmetrical spheres, this nebula is actually a tangle of multiple gas layers, each telling a different chapter of its dying star's violent final act. What makes M76 so fascinating isn't just its shape, it's the story written in those overlapping lobes. Hubble's razor-sharp imaging reveals at least 4 distinct shells of gas, each expanding at different speeds and angles. The outermost layers stretch unevenly, like a burst balloon frozen mid-explosion, while the inner regions twist into knots and braids. This isn't the orderly ejection of a star gently shedding its skin, it's the aftermath of a series of convulsions, as if the star couldn't decide how to die and instead left behind a fragmented memoir of its demise. The real clue to this chaos lies in the nebula's chemistry. Spectroscopic analysis shows dramatic variations in nitrogen and oxygen concentrations between the lobes, suggesting the star didn't expel its outer layers all at once. Instead, it coughed them up in fits and starts, with each eruption dredging up material from different depths of its interior. Imagine a volcano that doesn't just erupt once, but in staggered bursts, each spewing lava with a slightly different mineral composition. That's essentially what happened here, only instead of lava, it was superheated stellar plasma painting the cosmos in layered strokes. Then there's the central mystery: what caused such turbulent ejections? Most planetary nebulas form when a star's outer layers drift away steadily, driven by gentle radiation pressure. But M76's fractured structure hints at something far more dramatic: a binary companion. The nebula's bipolar lobes, those dumbbell shapes that gave it its name, are classic hallmarks of a star that didn't die alone. Theorists suggest a nearby partner could have siphoned off material, distorting the dying star's magnetic fields and funneling its outbursts into opposing jets. Yet curiously, no companion has been spotted. Either it's too faint to detect, or the star's own spin was so extreme it mimicked a binary's gravitational influence, whipping its death throes into this intricate frenzy. The little dumbbell's greatest irony might be its very name. What was once labeled for simplicity has become a benchmark for complexity, a reminder that the universe rarely fits into neat categories. Those delicate loops and braids aren't just debris, they're a stellar autopsy report waiting to be decoded. And as telescopes grow sharper, who knows how many more of these cosmic misnomers will reveal hidden depths, proving that sometimes the most unassuming objects hold the wildest secrets. The Bug Nebula hides its most explosive secret behind a thick veil of dust, a central star so blisteringly hot, it defies conventional models of stellar death. Officially catalogued as NGC 6302, this cosmic enigma might look like an intricate insect wing in visible light, but peel back the obscuring layers with infrared eyes, and you'll find one of the hottest stellar remnants ever recorded, blazing at a staggering 220,000 degrees Celsius. That's nearly 40 times hotter than our sun's surface, and it's rewriting our playbook for how stars transition into their final white dwarf phase. Buried deep within the nebula's dusty shroud, the star's extreme temperature tells a violent story. Most dying stars cool gradually as they shed their outer layers, but this one is doing the opposite, heating up at an unprecedented rate as its exposed core contracts under gravity's relentless pull. The process resembles a cosmic pressure cooker. As the star's outer atmosphere dissipates, its inner layers collapse inward, compressing and superheating like gas in a piston. But here's the twist. The bug's temperature is climbing faster than models predict, suggesting something unusual is happening beneath the surface. Spectroscopy reveals the culprit: runaway nuclear reactions in the star's helium shell. Normally, these reactions stabilize as a star dies, but in this case, they're spiraling out of control, creating thermal pulses so violent they're catapulting the star's temperature upward like a runaway elevator. Infrared observations from the Spitzer Space Telescope catch these convulsions in action. Flares of ionized carbon and oxygen bursting through the dust, each one a timestamp of the star's frenzied attempts to stabilize itself. It's as if the star is burning through its remaining fuel in panicked bursts rather than the slow, stately fade astronomers expected. Even more bizarre is what this means for the star's eventual fate. White dwarfs typically form over millennia as stars gently expel their outer layers, leaving behind cooling embers. But the bug's central star is racing through this process in cosmic fast-forward, its extreme heat accelerating the nebula's expansion and shredding the surrounding dust into intricate filaments. ALMA radio telescope data shows these dust clouds aren't just passively drifting. They're being actively sculpted by the star's radiation pressure, like sand-blasted glass frozen mid-etching. The real surprise, this chaotic heating phase might not be unique. Recent surveys suggest similar infrared bright stars lurk in other dusty nebulas, hinting that we've underestimated how often stars go out with a thermal tantrum rather than a whimper. The Bug Nebula's hidden heart isn't just a curiosity, it's a window into one of the universe's most explosive retirement plans, proving that even in their final moments, stars can defy expectations in the most spectacular ways. Deep in the constellation Leo, a dying star performs a magic trick that defies the laws of thermal physics. The frosty Leo Nebula, catalogued as ERAS 09371 plus 1212. This cosmic anomaly doesn't just glow with the usual warm hues of stellar death, it sparkles with actual ice crystals, a phenomenon so bizarre it left astronomers rubbing their eyes in disbelief. Imagine a candle flame surrounded by frost. That's the level of contradiction we're dealing with here. How could a nebula born from a star's searing final breaths become one of the coldest known places in the galaxy? The answer lies in a perfect storm of stellar mechanics and cosmic refrigeration. At first glance, the frosty Leo Nebula looks like any other planetary nebula. Its central star, now a white dwarf, illuminates swirling clouds of ejected gas. But peer through infrared telescopes and the scene shifts dramatically. Spectral lines reveal the unmistakable fingerprints of water ice, with temperatures plunging to negative 250 degrees Celsius, just 23 degrees above absolute zero. That's colder than the surface of Pluto, and it's happening right next to a star hot enough to vaporize diamonds. This thermodynamic paradox hinges on a rare alignment of conditions. The dying star didn't just shed its atmosphere, it practically flung it across space at breakneck speeds, creating a rapid expansion effect akin to the chill you feel when opening a pressurized can. The physics behind this cosmic deep freeze are as elegant as they are extreme. When the star first began its death throes, it ejected a slow-moving shell of gas rich in oxygen and hydrogen. Then, as its core contracted into a white dwarf, the star unleashed a second, much faster wind particles screaming outward at nearly 100,000 kilometers per hour. When this supersonic blast caught up with the earlier ejector, it didn't just push the material outward, it stretched it impossibly thin, like taffy pulled across light years. The sudden drop in pressure triggered an adiabatic cooling effect, the same principle that makes refrigerators work, but on a stellar scale. Gas that started at thousands of degrees found itself flash frozen in seconds, its water molecules locking into crystalline structures before they could reabsorb heat. But the frosty Leo's ice isn't just floating haphazardly. It's organized into a vast, clumpy disk encircling the central star, visible only in polarized light. This structure suggests another player in the cooling process, dust. Observations from the Spitzer Space Telescope show silicon-rich grains mixed throughout the nebula, each one acting like a microscopic ice nucleus. As water vapor condensed onto these particles, they formed icy mantles that further shielded the molecules from the star's heat. It's a cosmic version of the way snowflakes form in Earth's atmosphere, except here, the clouds are light years wide and the snow is interplanetary. Perhaps most intriguing is what the frosty Leo tells us about stellar afterlife. Most planetary nebulas dissipate within tens of thousands of years, but the presence of ice hints this one could linger far longer. These crystals aren't just passively cooling, they're actively reflecting the star's radiation back into space, creating a self-sustaining refrigeration cycle. Some models suggest regions of the nebula may remain frozen for millions of years, effectively turning it into a celestial icebox where complex chemistry could occur. That raises a tantalizing possibility. If similar icy nebulas seeded young solar systems with frozen water, they might have played a role in delivering the ingredients for life across the galaxy. The frosty Leo Nebula doesn't just challenge our understanding of stellar deaths, it redefines what's possible in the aftermath. It's proof that even in the universe's hottest furnaces, nature can carve out pockets of profound cold, crafting landscapes where fire and ice don't just coexist, they collaborate to create something utterly extraordinary. And as telescopes grow more sensitive to these frigid signatures, who knows how many more of these cosmic snow globes we'll find, each one a frozen masterpiece written in the glittering language of crystallized starlight. Fluffy, delicate, and almost translucent, the Cotton Candy Nebula drifts through space like a wisp of spun sugar caught in a cosmic breeze. Officially catalogued as NGC 7026, this ethereal structure defies the typical drama of planetary nebulas, trading fierce jets and sharp edges for a diffuse, cloud-like softness that seems to evaporate at the edges. Unlike its more flamboyant cousins, the Cotton Candy Nebula's beauty lies in its subtlety, a reminder that not all stellar deaths are violent spectacles. Some stars fade gently, their final breaths unfolding in slow motion, leaving behind structures so faint they barely cling to visibility. What creates this nebula's ghostly texture? The secret lies in the languid pace of its formation. Most planetary nebulas owe their vivid shapes to high-speed stellar winds, torrents of particles screaming outward at thousands of kilometers per second, carving sharp boundaries in the interstellar medium. But NGC 7026's central star opted for a different farewell. Observations reveal its winds meander outward at a leisurely pace, barely topping a few hundred kilometers per second. This sluggish expansion allows ejected material to drift apart like smoke from a doused candle, diffusing into threadbare veils rather than piling up into dense walls or filaments. The result is a nebula that behaves more like a fog bank than a fireworks display. Hubble's sensitive instruments capture tendrils of gas so tenuous, they're barely denser than the surrounding void, stretching light years across space yet containing less mass than a small moon. These gossamer strands glow predominantly in oxygen and hydrogen emission lines, their faint blue and pink hues reminiscent of Earth's auroras. But here's the twist: despite their fragile appearance, these wisps are anything but ephemeral. Radio telescope data suggests they've persisted for nearly 12,000 years, their longevity a testament to the nebula's isolation. Floating in a sparse region of the galactic arm, NGC 7026 faces minimal disruption from interstellar winds, allowing its delicate structures to endure like dust motes in a sunbeam. Yet the Cotton Candy Nebula's tranquility hides a thermodynamic paradox. At its heart lies a white dwarf burning at a respectable 90,000 degrees Celsius, hot enough to ionize the surrounding gas, but not enough to aggressively push it outward. This delicate equilibrium creates a nebula that's neither actively energized nor passively fading. Instead, it exists in a kind of stellar limbo, where gas dissipates just fast enough to avoid collapsing back inward, but slowly enough to maintain its dreamy, cloud-like aesthetic. What makes NGC 7026 truly remarkable is how it challenges our assumptions about stellar winds. Textbook models suggest dying stars should either roar or whisper, expelling material in violent bursts or barely perceptible breezes. But this nebula demonstrates a third option, a sustained, gentle exhale that threads the needle between drama and dissolution. It's proof that the universe has more retirement plans for stars than we've accounted for, and that sometimes the quietest exits leave the most hauntingly beautiful remnants. Stretched across the cosmic canvas like a celestial hourglass split at the seams, the Peanut Nebula presents astronomers with a structural riddle wrapped in luminous gas. Officially catalogued as NGC 2371, this bipolar nebula's central region doesn't follow the usual rules of symmetry. Instead, it's warped into a chaotic knot of glowing filaments, as if some unseen hand grabbed the nebula's waist and twisted. While most planetary nebulas exhibit elegant axial symmetry around their central stars, the Peanut's core resembles a cosmic taffy pull. its geometry mangled by forces we're still struggling to decipher. Peering into this stellar wreckage, Hubble's sharp vision reveals two dominant theories vying for explanation. The first points to magnetism's invisible hand, a stellar magnetic field gone rogue during the star's death throes. As the aging star shed its outer layers, its remaining core spun faster, amplifying any pre-existing magnetic fields like a dynamo. These fields could have acted as cosmic puppet strings, channeling the outgoing gas into opposing jets while simultaneously twisting the inner regions into that signature peanut shape. Supporting this idea are telltale braided filaments near the core, their spiral patterns mirroring the helical structures seen in laboratory plasma experiments when magnetic fields dominate particle flows. If correct, the Peanut Nebula might be nature's most dramatic demonstration of how magnetism can sculpt chaos into eerily precise forms across light years of space. Yet competing observations suggest a second, equally compelling culprit: gravitational sabotage by a hidden companion star. The nebula's central white dwarf exhibits peculiar velocity shifts, tiny wobbles in its position that hint at an unseen object tugging on it. Simulations show that if a second star orbited close enough during the nebula's formation, its gravity could have warped the ejector disk like a vinyl record left in the sun, distorting the outflow into those observed kinks and bends. Intriguingly, the nebula's western lobe expands slightly faster than its eastern counterpart, a telltale signature of asymmetric gravitational influence. Some researchers go further, proposing the companion might have been shredded during the primary star's death throes, its remains leaving behind gravitational scars that continue shaping the nebula's chaotic core. The debate intensifies when examining the nebula's chemical fingerprints. Spectroscopic analysis reveals unexpected nitrogen concentrations along the twisted central axis elements typically forged deep within a star's core. Their presence in these warped regions suggests violent mixing during ejection, consistent with either magnetic upheaval or gravitational stirring from a companion. ALMA telescope data adds another layer. The twisted zone harbors dense molecular clumps moving at odd angles to the main outflow, like eddies in a river where two currents collide. Whether these represent magnetic confinement zones or the splashes from a stellar partner's disruptive passage remains astronomy's version of a forensic showdown. What makes NGC 2371 particularly fascinating is how its enigma challenges our classification systems. Most bipolar nebulas fall neatly into either magnetically collimated or binary influence categories, but the Peanut's distorted core displays hallmarks of both. This ambiguity forces us to consider whether these sculpting mechanisms might coexist more often than assumed, perhaps with magnetism dominating the large-scale jets while a companion's gravity tweaks the finer details. Future observations aiming to detect residual magnetic fields or hunt for the hypothetical companion's infrared glow could finally crack this case. Until then, the Peanut Nebula stands as a delicious cosmic paradox, reminding us that even in death, stars resist simple explanations, preferring instead to leave behind twisted puzzles for us to unravel. The etched hourglass nebula, known to astronomers as Mycen 18, presents one of the most striking examples of cosmic symmetry, a pinched waist so precisely sculpted, it looks like a celestial timepiece suspended in space. But this breathtaking shape isn't just a quirk of stellar winds, it's the handiwork of an invisible force powerful enough to bend gas to its will. Magnetic fields twisting through the nebula like unseen tendons have compressed its midsection into that iconic hourglass figure, raising a fascinating question. Why do some hourglass nebulas like Mycen 18 owe their shape to magnetism while others form purely through the push and pull of stellar winds? The secret lies in the nebula's central star, a white dwarf spinning at breakneck speeds. As the star shed its outer layers, its rapid rotation amplified its magnetic fields, turning them into cosmic sculpting tools. These fields didn't just guide the outflowing gas, they actively collimated it, funneling material into two opposing jets while constricting the waste like a cosmic corset. Hubble's polarizing filters reveal the magnetic fingerprints clearly, looping lines of force visible in the alignment of dust grains, tracing paths that mirror the nebula's dramatic pinch. Unlike the chaotic, wind-driven hourglass shapes of nebulas like the southern crab, my CN18's structure is precision itself. Its symmetry so exact it could pass for an engineered artifact rather than a product of celestial chaos. What makes this magnetic sculpting even more remarkable is its longevity. Most planetary nebulas see their magnetic fields dissipate as their central stars slow down. But my CN18's fields have persisted, their influence etched permanently into the nebula's architecture. Spectroscopic studies show ionized gas streaming along these magnetic channels even now, like water flowing through an invisible aqueduct. The result is a nebula that defies the usual fate of expansion. Its waist remains sharply defined, resisting the blurring effects of time. Compare this to the Butterfly Nebula, another hourglass structure, but one shaped primarily by stellar winds. Without strong magnetic fields to constrain it, the butterfly's waist is broader, its contours softer, as if the gas were allowed to spill outward more freely. The difference between these two nebulas is like comparing a tightly laced violin string to a drifting plume of smoke, one shaped by tension, the other by turbulence. Yet the etched hourglass doesn't just challenge our understanding of nebula formation, it hints at a deeper mystery. Why do some dying stars generate such powerful magnetism while others fade without leaving a magnetic mark? Some theories suggest binary companions might be the key, their gravitational dances spinning up the dying star like a cosmic top, juicing its magnetic fields in the process. Others propose it's a matter of stellar composition, with metal-rich stars more likely to leave behind magnetic remnants. Whatever the reason, my CN18 stands as a cosmic Rosetta Stone, a clue that magnetism, often overlooked in stellar deaths, might play a far greater role in shaping the universe's most beautiful structures than we ever imagined. Rising from the cosmic dust like a neon sign suspended in the void, the red rectangle nebula presents a geometric puzzle that defies nature's usual preference for organic shapes. Catalogued as HD 44179, this celestial structure stretches across interstellar space with the crisp angles of a stained glass window, its luminous X shape so precise it looks laser-etched against the darkness. Most dying stars leave behind swirling clouds or delicate bubbles, so how did this one craft what appears to be a cosmic blueprint? The answer lies in the relentless gravitational tug of war between two stars locked in a dance that's equal parts destructive and artistic. At the nebula's heart, a binary system spins in furious harmony, a dying red giant and a smaller companion star orbiting so close, their gravitational forces act like cosmic chisels. As the red giant shed its outer layers, its partner's gravity didn't just pull material away, it sculpted the outflow into that iconic X shape. Here's how it works. The smaller star's orbit carves a dense, flat disk of dust around the primary star, funneling ejected gas into two opposing cones above and below this plane. But the magic happens where these cones intersect our line of sight, their edges overlapping to form those razor-straight diagonal lines. It's the astrophysical equivalent of shining a flashlight through a slitted screen, except here, the flashlight is a star's dying breath, and the screen is a cosmic whirlpool of dust and gravity. Hubble's sharp gaze reveals even stranger details. The red rectangles rungs those ladder-like crossbars within the X aren't static features. They're shock waves frozen in time, created as periodic bursts from the central star's slam into slower moving gas. Spectroscopy shows these rungs glow with the signature of polycyclic aromatic hydrocarbons, complex carbon molecules more commonly found in interstellar smoke clouds than in planetary nebulas. Their presence here suggests the binary stars aren't just shaping the nebula, they're seeding it with the building blocks of organic chemistry. The real enigma lies in the system's symmetry. Unlike the Butterfly or ant nebulas, where jets curve and twist, HD 44179's structure remains eerily rigid, its angles barely deviating over decades of observation. This precision hints at an unseen stabilizing force, possibly a magnetic field generated by the star's orbital motion, acting like invisible guy wires to keep the outflow channels locked in place. Supporting this theory, radio telescopes have detected polarized light patterns consistent with magnetic influence, tracing ghostly lines of force that align perfectly with the nebula's geometric arms. Yet the red rectangle's most startling revelation came when astronomers noticed its central star isn't just dying, it's burning lithium. This fragile element is typically destroyed in stellar interiors, making its presence here as unexpected as finding ice in a furnace. The likely explanation: the companion star's gravity is ripping material from the red giant's surface faster than it can fuse, dredging up lithium that would otherwise vanish into the nuclear fires. This makes the system a kind of cosmic alchemy lab, where stellar death inadvertently preserves ingredients normally annihilated in the process. What emerges is a portrait of stellar demise unlike any other, a death so meticulously choreographed it transforms chaos into geometry. The red rectangle challenges our notion of what's natural in the cosmos, proving that under the right conditions, even the messiest processes can yield precision worthy of a master architect. As we decode its secrets, one thing becomes clear: this isn't just a nebula. It's a testament to the universe's hidden talent for turning celestial violence into art, one gravitational interaction at a time. Most planetary nebulas race outward at breakneck speeds, their gases shredding through space like fireworks against the night. But the Turtle Nebula refuses to be rushed. Catalogued as NGC 6210, this cosmic anomaly creeps along at a mere 19 kilometers per second, less than half the expansion velocity of typical planetary nebulas. It's as if the universe hit the brakes on this stellar farewell, leaving astronomers puzzling over what could possibly slow a dying star's explosive outburst to this leisurely pace. The secret might lie in the nebula's progenitor, the star that birthed it. Unlike massive stars that detonate violently, lower mass stars like our Sun tend to bow out more gently. The Turtle's sluggish expansion suggests its parent star could have been a lightweight, barely tipping the scales at 1 solar mass or less. Such stars lack the gravitational muscle to launch their outer layers with much force, resulting in these slow-motion ejections. Hubble images support this theory, revealing a nebula with delicate, finely layered shell structures that form when material drifts away gradually rather than being blasted outward. But here's where the plot thickens. The nebula's innermost regions tell a different story. High-resolution spectroscopy reveals pockets of gas moving significantly faster than the rest, hinting at sporadic bursts of acceleration buried within the overall crawl. This unevenness points to another intriguing possibility: hidden braking mechanisms at work. Some researchers propose magnetic fields could be acting like cosmic rains, tethering the expanding gas and slowing its progress. Others suspect a companion star's gravity might be siphoning off momentum, leaving the nebula's outer edges to drift rather than sprint. The Turtle's central star adds another layer to the mystery. Unlike the scorching white dwarfs found in most planetary nebulas, this one burns at a relatively cool 50,000 degrees Celsius, another clue pointing to a low-mass origin. Yet it sports bizarre chemical fingerprints, including elevated levels of nitrogen and helium, as if its surface was dredged up from deeper layers during its death throes. This unusual composition could explain the nebula's strange kinematics. Elements heavier than hydrogen might resist expansion more stubbornly, like syrup flowing compared to water. Perhaps most fascinating is what the Turtle Nebula implies about stellar timelines. While most planetary nebulas dissipate within tens of thousands of years, NGC 6210's slow expansion suggests it could linger for hundreds of millennia, a fossil of stellar death preserved far longer than its flashier counterparts. This endurance makes it a prime candidate for studying long-term nebula evolution, offering clues about how these structures interact with interstellar space over cosmic timescales. The turtle doesn't just challenge our assumptions about stellar deaths, it redefines what's possible in their aftermath. In a universe that often favors spectacle, this nebula reminds us that sometimes the most revealing stories unfold not with a bang, but with the quiet, stubborn persistence of a star determined to leave its mark on its own terms. Among the countless planetary nebulas scattered across our galaxy, the Water Lily Nebula stands out with an almost improbable gift. Its polar jets point directly at Earth, giving us a front-row seat to one of nature's most precisely aligned cosmic explosions. Officially known as M192, this celestial rarity doesn't just dazzle with its petal-like lobes, it offers astronomers an unparalleled opportunity to study the inner workings of high-velocity stellar winds with a clarity no other nebula can match. Most bipolar nebulas tilt at oblique angles, their intricate structures partially obscured by perspective. But the Water Lily's jets fire straight down our line of sight, like staring into the barrel of a cosmic cannon. This exact alignment lets telescopes dissect the outflow's velocity, chemistry, and shock dynamics with forensic precision. Every ripple in those luminous streams becomes a data point, revealing how material ejected at nearly 700 kilometers per second interacts with slower-moving gas expelled earlier in the star's death throes. Imagine having a particle accelerator stretched across light years of space, except nature built this one for free, and it comes with a built-in light show. What makes this orientation especially valuable is the way it exposes the jet's internal structure. Normally, astronomers have to infer these details from side views, piecing together 3D models from flattened images. Here, we see the full depth of the outflows, right down to the central star's rotational axis. Hubble's spectroscopy reveals nested layers within each jet, fast-moving cores surrounded by slower sheaths, all threaded by helical magnetic fields visible as faint corkscrew patterns in polarized light. It's as if the dying star left behind a set of perfectly aligned cosmic blueprints, showing exactly how it funneled its final breaths into space. The Water Lily's pole on view also solves a long-standing mystery about how such jets stay collimated over vast distances. Without the distortion of angled perspectives, researchers can track how shock waves propagate along the outflows, maintaining their narrow beams despite the chaotic environment. Recent radio observations from ALMA pinpointed rhythmic brightness variations along the jet's subtle pulsations, matching theoretical predictions of how central stars can step on the gas in discrete bursts rather than a continuous stream. These findings don't just apply to M192, they're rewriting our understanding of how all aspherical nebulas maintain their shapes against the dissipating pressures of interstellar space. Yet the Water Lily's greatest scientific treasure might be the snapshot it provides of a fleeting cosmic phase. Most planetary nebulas transform dramatically as they expand, their structures blurring over millennia. But this nebula's alignment freezes a critical moment in stellar evolution, the precise instant when a dying star transitions from chaotic mass lost to focused jet ejection. That frozen moment is packed with chemical clues too. Embedded within the jets are rare molecular ions like H3+, a fragile triatomic hydrogen variant that can't survive for long in most nebulas. Its presence here confirms theoretical models predicting brief but intense chemical activity during jet formation, a process we'd likely miss in less optimally oriented systems. The Water Lily Nebula doesn't just defy astronomical odds with its perfect orientation. It turns chance alignment into an irreplaceable laboratory. Every photon reaching our telescopes carries undistorted information about physics too extreme to replicate on Earth, processed through nature's finest lens, a perfectly aligned stellar farewell. And as instruments grow more sensitive, this cosmic pulse, I may yet reveal deeper secrets: how magnetic fields sculpt dying stars' last acts, how complex molecules form in stellar winds, even how the universe itself engineers such precision amid the chaos of stellar death. For astronomers, that's not just luck. It's like finding the universe's instruction manual open to the most important page. Amid the glowing remnants of a dying star, the Mimosa Nebula hides an olfactory surprise, a celestial perfume of complex organic molecules drifting through its sculpted gases. Officially designated NGC 5189, this cosmic bloom doesn't just dazzle the eyes with its intricate S-shaped ribbons of ionized oxygen and nitrogen. It teases the imagination with a chemical cocktail that, under the right conditions, might resemble the faintest whiff of a floral fragrance. Spectroscopy reveals a startling array of carbon-based compounds, including polycyclic aromatic hydrocarbons and even simple sugars, molecules that on Earth are building blocks for life. But how could such delicate structures survive the violent death throes of a star? The answer lies in the nebula's unique expansion history, where layers of ejected material act like insulating blankets, shielding these fragile molecules from the white dwarf's searing radiation. What makes the Mimosa's chemistry truly extraordinary isn't just the presence of organics, it's their distribution. Unlike most planetary nebulas where harsh ultraviolet light breaks down complex molecules, NGC 5189's spiraling structure creates sheltered pockets. Imagine a cosmic greenhouse. The nebula's densest filaments absorb and scatter harmful radiation, while cooler regions between the folds provide safe havens for molecular assembly. ALMA telescope data pinpoints these reservoirs clearly, clumps of acetylene and hydrogen cyanide nestled in the nebula's shadowed arcs, remnants of the star's carbon-rich outer layers that escaped complete destruction. This raises a tantalizing possibility. If nebulae like the Mimosa can preserve and disperse organic molecules across interstellar space, could they be cosmic couriers, delivering life's raw materials to newborn star systems? Observations suggest these carbon compounds aren't just sitting idle, they're hitching rides on dust grains, which act as miniature spaceships ferrying them through the galaxy. When these grains eventually plunge into the protoplanetary disks of young stars, they could seed burgeoning worlds with probiotic ingredients. It's a theory supported by meteorite samples on Earth, which contain similar organic molecules locked within their ancient rock, hinting that our own planet might have been seasoned with stardust from long-dead stars like the one at the Mimosa's heart. Yet the nebula's role in astrobiology isn't its only marvel. The very existence of such complex chemistry in what should be a sterile environment challenges our understanding of molecular resilience. Laboratory experiments show that polycyclic aromatic hydrocarbons, the same compounds found in soot and smog on Earth, can withstand temperatures that vaporize most other matter. In the Mimosa's case, these rugged molecules may have formed in the star's cooler outer atmosphere before ejection, their ring-like structures making them exceptionally stable. Their survival offers a clue to how organic chemistry persists in even the most hostile corners of the universe, knitting together atoms in defiance of the chaos around them. The Mimosa Nebula doesn't just illuminate how stars die, it hints at how their ashes might contribute to life's cosmic recipe. As telescopes grow more adept at detecting subtle molecular signatures, we're left to wonder, how many other celestial gardens are out there, quietly cultivating the ingredients of existence? And if nebulae like this one have been scattering such seeds for billions of years, could the universe be far more fertile than we ever imagined? From the Butterfly Nebula's magnetic wings to the frosty Leo's impossible ice, these 30 discoveries have shattered every assumption we once had about how stars die. We've seen nebulas flicker like faulty light bulbs, defy gravity with peanut-shaped twists, and even freeze themselves into cosmic snow globes. Each one is a reminder that stellar death isn't just an ending. It's a metamorphosis where physics bends into art and chaos births beauty we're only beginning to comprehend. Take the Helix Nebula, where a star's final act strung cosmic diamonds across the void, or the Ant Nebula. its supersonic jets carving space with laser precision. The Calabash Nebula's rotten egg stench and the water lily's perfectly aligned jets prove that the universe has a flair for the dramatic, blending violence and elegance in ways that leave even seasoned astronomers speechless. And who could forget the Medusa Nebula, a ghost so faint it whispers rather than glows, challenging our very definition of what a nebula can be. These aren't just celestial oddities, they're cosmic puzzles rewriting our textbooks. The Stingray Nebula's rapid aging, the Bug Nebula's hidden furnace, and the red rectangle's geometric perfection all force us to ask, how many more rules are there left to break? If stars can die in slow motion like the Turtle Nebula or flash freeze like the Boomerang, what other extremes are lurking in the darkness? So tonight, when you look up at the stars, remember, what seems like a static speck of light might be a stellar swan song, a masterpiece unfolding over millennia. Maybe it's the Helix's eerie eye, the cat's eye's layered explosions, or the cotton candy's delicate haze that captures your imagination. Whatever it is, let it remind you, the universe is stranger, wilder, and more inventive than we ever dreamed. Now it's your turn. Tell us in the comments which nebula left you in awe, and what cosmic mystery do you hope we unravel next? The night sky isn't just a spectacle, it's an invitation to wonder. And with discoveries like these, who knows what we'll find when we dare